Today we'll discuss nucleophilic substitution reaction in haloarenes. Now when we compare haloarenes and haloalkenes, haloarenes does not undergo nucleophilic substitution reaction as fast as haloalkenes. What is the reason why haloarenes does not undergo nucleophilic substitution reaction as fast as haloalkenes? Let us see. Haloarenes does not undergo nucleophilic substitution reaction as fast as haloalkanes. In haloalkanes, the reaction was very fast. At normal temperature itself, haloalkanes used to undergo nucleophilic substitution reaction. But haloarenes does not undergo nucleophilic substitution reaction as fast as haloalkanes. The first reason you see here, I'm just taking chlorobenzene. Now in chlorine there is what? Lone pair of electron. This lone pair of electron on chlorine atom is involved in conjugation with the pi electron of benzene ring. In general we can say it is involved in what? Resonance. And here it's what type of resonance? It is pulsar effect. Why it is pulsar effect? Because the halogen atom is giving electron to the benzene ring. So it's known as what? Pulsar effect. So these are the resonating structures. Now due to resonance, what happens? The carbon halogen is getting what? Partial double bond character. Got it? So the lone pair of electron on halogen is involved in conjugation with the pi electron of benzene ring, due to which the carbon halogen gets a partial double bond character. Now if you take haloalkane, taking chloromethyl chloride, here is resonance possible. Here resonance is not possible. So that is the first reason why haloarenes does not undergo nucleophilic substitution reaction as fast as haloalkane. That is, first reason is what? Resonance stabilization. Resonance stabilization. So carbon halogen gets partial double bond character. But in haloalkane there is no resonance stabilization. So we know it is difficult to break the energy required to break a double bond is more than the energy required to break a single bond. So that is the first reason. The carbon halogen gets partial double bond character due to resonance stabilization. This effect is not there in haloalkane. Now the second reason. Now if you take the carbon atom in haloarene, the carbon atom is in which hybridization? It is in sp2 hybridization. And in haloalkane, it is in which hybridization? sp3 hybridization. So which is more electronegative? sp2 hybrid carbon is more electronegative than sp3 hybrid carbon. That is, an sp2 hybrid carbon is more electronegative than sp3. Why? Greater the s character, more close it is towards the nucleus, because s orbital is close to the nucleus. So greater the s character means it's more attracted towards the nucleus. Here the s character is more and here the s character is what? Less, because total 100%, in that 3 are what? P orbitals. So just it is only 25% is what? S character. So an sp2 hybrid carbon is more electronegative than sp3 hybrid carbon. When the electronegativity is more, the tendency to give electron will be what? Less. So sp2 hybrid carbon will not give easily electron compared to what? sp3. So that is the second reason. That is, in haloarenes, the carbon atom is in sp2 hybrid state, and in haloalkane it is in which hybridization? sp3. So sp2 hybrid carbon is more electronegative than sp3 hybrid carbon. So that is the second reason. And the third one is the carbon halogen bonds polarity. Now due to partial double bond character, what happens here? The polarity decreases. That is, the tendency to give electron decreases in what? Haloarenes. Okay. Then the fourth one is, see here, now after the bond cleavage, the carbocation formed is what? It's phenyl carbocation. Now this phenyl carbocation, if you see here, resonance is not possible, no resonance. Why? Because the positive charge and the double bond is coming in the same carbon atom. So here no resonance, hence cannot proceed by Sn1 reaction. So hence cannot proceed by Sn1 reaction. That is, the phenyl cation formed is not resonance stabilized, hence cannot proceed by Sn1 reaction. Next you see here, the benzene ring itself is what? Having high electron density. So that itself is acting as what? Nucleophile. So the incoming nucleophile, instead of experiencing attraction, it will experience what? Repulsion. Next. Due to high electron density of phenyl group, incoming nucleophile experiences repulsion. So these are the 4 reasons why haloarenes does not undergo nucleophilic substitution reaction as fast as haloalkanes. One is resonance stabilization. The lone pair of electron on halogen is involved in resonance with the pi electron of benzene ring, due to which it gets what? Partial double bond character. And this effect is not there in haloalkanes. Then the second reason is the carbon atom in haloarene is in which hybridization? sp2, and in haloalkane it is what? sp3. So sp2 hybrid carbon is more electronegative than sp3 hybrid carbon. Next is the polarity of carbon halogen bond decreases in case of haloarene, again due to what character only? Double bond character. Then the fourth reason is the phenyl cation formed is not resonance stabilized. Why it's not resonance stabilized? Because the positive charge and double bond comes in the same carbon atom. So it cannot proceed by which mechanism? Sn1 mechanism. Then next you see benzene itself, the phenyl group, it's having what? High electron density, because the electron density inside the benzene ring is high. So that itself is acting as what? Nucleophile. So the incoming nucleophile also will experience what? Repulsion instead of what? Attraction. So these are the 4 reasons why haloarenes does not undergo nucleophilic substitution reaction as fast as haloalkanes. In case of haloalkane, there is no resonance stabilization. So carbon halogen is not getting double bond character. So polarity is more, and then the hybridization of the carbon is what? sp3, and the carbocation formed easily proceeds by what? Sn1 reaction or Sn2 reaction. Then the electron density on the alkyl group is also what? Less compared to what? In the benzene ring. Due to high electron density of benzene ring, incoming nucleophile experiences what? Repulsion. So these are the reasons why haloarenes does not undergo nucleophilic substitution reaction as fast as haloalkanes. Let us see a few examples of nucleophilic substitution reaction in haloarenes. See, chlorobenzene I am taking, and I am taking CH3, CH2, Cl. Now this, when treated with aqueous KOH, that is at normal temperature, what is the product? CH3, CH2OH, you are getting an alcohol. Now the same reaction here, I am going to treat it with sodium hydroxide at 623 Kelvin, 300 atmosphere pressure, followed by acidification. Then only Cl is being replaced by OH. So got the difference? That is, both the cases, this is also nucleophilic substitution reaction, this is also nucleophilic substitution reaction. Here directly at room temperature, when you are treating it with aqueous KOH, you are getting what? Ethanol. But here what is happening? The same reaction, you are treating it with sodium hydroxide at 623 Kelvin, 300 atmosphere pressure, followed by acidification, then only Cl is being replaced by what? OH. So got the difference? So the reasons also already I had explained. So that are the reasons why haloarenes does not undergo nucleophilic substitution reaction as haloalkene. And this reaction is known as dose process. Dose process. And in case of dose process, you can take only chlorobenzene. You can't take iodobenzene or bromobenzene. Its dose process is what? Chlorobenzene reacts with NaOH at 623 Kelvin, 300 atmosphere pressure, followed by acidification to give you what? Phenol. You can't take bromobenzene or iodobenzene. Now the same thing, I'm just going to write a few reactions here. See here. I'm introducing a NO2 group at the para position, okay. Then I'm going to treat it with sodium hydroxide and the temperature required is 440 Kelvin followed by acidification. So the product you're going to get is phenol. And you have at para position NO2 group, okay. Then next what I'm going to do is, again in ortho position also I'm going to put a NO2 group. This again I'm going to treat it with NaOH. Here the temperature is required is 368 Kelvin followed by acidification. So the product formed is OH, NO2, NO2. It is 2,4-dinitrophenol. Next here you see both the ortho positions and the para position I have introduced. I have put NO2 group. Here just have to warm with water and you are getting phenol. Okay. Then another one you see here. I am introducing NO2 group in the meta position. And here the condition is followed by acid. So I have written these few reactions. What do you observe here? When I have introduced an electron withdrawing group at para position, the temperature from 623 Kelvin, it has reduced to what, 440 Kelvin, and you haven't to supply any pressure. And it's in which position? It's in para position. Then again I have introduced one more electron withdrawing group at the ortho position. In that case again the temperature has been decreased to 368 Kelvin. Now in this reaction, both the ortho position and para position you have an electron withdrawing group, and in this case normal water is enough. You don't even require what, an alkali, and you're getting Cl replaced by what, OH group. And in this case I have introduced a electron withdrawing group in which position? Meta position, but the condition remains the same. So why is this difference? Now listen here carefully. Due to resonance, the electron density is increasing in which position? Ortho and para position. So that electron is withdrawn by whom? The electron withdrawing group. So what happens to the resonance effect? It weakens. So the cleavage of carbon halogen bond will take place easily. So is it clear? That is, if you introduce an electron withdrawing group in ortho or para position, the ability of nucleophilic substitution reaction in haloarenes becomes fast. Why? Because this electron withdrawing group withdraws the electron and the ability or the effect of resonance becomes what? Less. So the cleavage of carbon halogen bond becomes easy. So that is the reason why para-nitrochlorobenzene undergoes nucleophilic substitution reaction faster than what? Chlorobenzene. Then again I have put another NO2 group in which position? Ortho. That is, you have an electron withdrawing group at ortho as well as para position. In such a case, the temperature required is less because both of them are withdrawing what? Electrons. So the resonance effect is becoming what? Very slow, or the intensity is becoming less. Here you see how many electron withdrawing groups are there? 1, 2, 3. 2 in ortho and 1 at para. So all the 3 are withdrawing electrons. So what happens to the resonance? It becomes what? Nearly negligible. So the bond cleavage becomes easy. So you can just use normal water. You can just warm it with water and then Cl is being replaced by what? OH. But now see in this case, what do you observe? NO2 is there, an electron withdrawing group is there, but the condition remains what? Same. Why? The electron withdrawing group is present in which position? It is present in meta position. Is the electron density increasing at meta position due to resonance? The electron density is not increasing in meta position due to resonance. It's increasing in which position? It's only increasing in the ortho and para position. So if you put an electron withdrawing group in meta position, the resonance is not being affected. So the resonance is there. So carbon halogen will get what? Double bond character. So you have to use the same condition as what we have used in what? Chlorobenzene. So is it clear? So if an electron withdrawing group is present in ortho or para position, nucleophilic substitution reaction in haloarene becomes fast. Why? Because the intensity of resonance effect becomes less, because the electron withdrawing groups withdraws electron and makes nucleophilic substitution reaction faster. So is it clear? Next we'll see electrophilic substitution reaction in haloarenes. Now when you compare haloarenes and benzene, haloarenes does not undergo electrophilic substitution reaction as fast as benzene. The reason is what you see. In case of haloarenes, the lone pair of electron is involved in conjugation with the pi electron of benzene ring, and that effect is known as which effect? Plus R effect. And due to plus R effect, the electron density is increasing in the benzene ring. Next you see, in case of haloarenes, Cl is halogens are electron withdrawing group. So they withdraw electron from the benzene ring, and that effect is known as which effect? Minus I effect. Now when you compare plus R effect and minus I effect, the minus I effect is greater than plus R effect. That is, minus I effect dominates plus R effect. So what happens to the electron density in the benzene ring? It is decreasing. But this effect is not there in benzene. So that is the reason why benzene undergoes electrophilic substitution reaction faster than what? Haloarenes. That is, in case of haloarenes, the lone pair of electron in halogen is involved in conjugation with the pi electron of benzene ring, and that effect is known as plus R effect. Why? The electron is flowing from the halogen towards the benzene ring. So the electron density is increasing where? In the benzene ring. At the same time, halogen is what type of group? Electron withdrawing group. So that effect is known as which effect? Minus I effect. They are taking electrons from the benzene ring. So what is happening to the electron density in the benzene ring? It is decreasing. When you compare minus I effect and plus R effect, minus I effect dominates plus R effect. So the electron density in the benzene ring is decreasing. So haloarenes undergo electrophilic substitution reactions slower than what? Benzene. Is it clear? So we'll see the examples of electrophilic substitution reaction. Now, if you take chlorobenzene, if you are treating it with chlorine in presence of halogen carrier, anhydrous ferric chloride in dark, the reaction is carried in dark, the product will be what? Because already we have discussed the electron density is increasing in which position? Ortho and para. So the attack of the electrophile takes place in the ortho and para position. So you are getting ortho dichlorobenzene and para dichlorobenzene. Now I am just going to take next bromobenzene. Okay. So this when treated with bromine in presence of anhydrous ferric bromide, what will you get? Ortho dibromobenzene and para dibromobenzene. Next you see nitration. What is the nitrating mixture? All this you have discussed in studied in class 11. Concentrated H2SO4, concentrated HNO3. The attacking nucleophile is what? NO2. So you'll get orthonitrochlorobenzene and para-nitrochlorobenzene. Then is sulfonation. When treated with concentrated sulfuric acid, the attacking electrophile is what? SO3H. So you get orthochlorobenzene sulfonic acid and para-chlorobenzene sulfonic acid. So these are the examples of what? Electrophilic substitution reaction. Chlorination, bromination, nitration, sulfonation. Next we will go to is Friedel-Crafts alkylation reaction. What is Fittig reaction? Haloarenes reacts with metallic sodium and dry ether. in presence of dry ether. So what is eliminated? Halo, sodium halide, and you get is diphenyl plus NaX. So what is the Fittig reaction? Haloarenes reacts with metallic sodium in presence of dry ether to give you what? Diphenyl or bisphenyl. So this is known as Fittig reaction. Next comes is Wurtz-Fittig reaction. In this, haloarene reacts with haloalkane. General I am writing RX, haloalkane in presence of metallic sodium and dry ether. So you will get what? Alkyl benzene is the product. Alkyl benzene plus NaX. So that is known as what? Wurtz-Fittig reaction. That is, you are taking the reactant of Wurtz reaction and Fittig reaction. Haloarene is reacting with haloalkane in presence of metallic sodium and dry ether to give you alkyl benzene is known as Wurtz-Fittig reaction. Now we will discuss few questions. Now see, I am going to write here a equation. NBuBr plus KCN alcoholic gives NBuCN plus KBr. Now the question is to propose a mechanism. You have to propose a mechanism for this reaction. Now see, when they are asking you to propose the mechanism, you just see what is the haloalkane given to you. N-butyl bromide. So this is what? Primary. And primary haloalkanes proceeds only by Sn2 mechanism. Okay. So first step, what are you going to write? It proceeds by Sn2 mechanism as it is a primary haloalkane. Okay. So this is what you are going to write. Then you are going to make the structure. So here hydrogen, hydrogen. Here what will come? Br, and here what will come? C3H7. Now what is the nucleophile? It's Cn minus. So in case of Sn2 mechanism, the nucleophile attacks the carbon pairing halogen from a side just opposite to the carbon halogen bond, which results in the formation of what? Transition state. Then the transition state is converted into product. So what is happening to the configuration of the product? It is getting inverted. But is it optically active? This is optically inactive. But in case of Sn2 mechanism, if it is optically active or optically inactive, there is what? Inversion of configuration. So this is how you have to write the mechanism. So this is a primary haloalkane, and primary haloalkane proceeds only by which mechanism? Proceeds by Sn2. And before starting the mechanism, you have to write it. It proceeds by which mechanism, that you have to specify. So next one question I am going to give you. CH3 thrice CBr plus KOH aqueous gives you CH3 thrice COH plus KBr. So here also you have to propose a mechanism. Now see, what is the haloalkane? It is a tertiary, and tertiary always proceeds by which mechanism? It proceeds only by Sn1 mechanism. So here you are going to write what? It proceeds by Sn1 mechanism. So what is the first step in Sn1 mechanism? Cleavage of carbon halogen bond. So here it's cleavage of what? Carbon bromine bond. So one you are going to write cleavage of carbon bromine bond. So we'll get what? CH3, 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 Br. And you know it's what type of step? It's a slow step. So it results in the formation of what? The carbocation. So this is the first step. Next step is what? Attack of nucleophile. Which is the nucleophile? OH minus. Next is attack of nucleophile OH minus on the carbocation. Plus OH minus, and it's what step? It's fast step. So I'll get the product CH3, 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 OH. So is it clear? Tertiary will proceed only by Sn1 reaction and primary will proceed only by what? Sn2. Then the problem comes with which one? Secondary. Secondary proceeds both by Sn1 and Sn2 depending upon the nucleophile. If it's a strong nucleophile, it will proceed by Sn2, and if the nucleophile is slightly weak, it proceeds by what? Sn1. So in that case, they will specify it's proceeding by which mechanism. And in case of optically active means, if it is proceeding by Sn1, they'll say the product formed will be what? Racemic mixture. And if it is Sn2 means, it will always be what? Inversion of configuration. Next, let us do some conversions. So I'm writing here, you have to convert toluene to phenyl acetic acid. Toluene to phenyl acetic acid or alpha phenyl acetic acid. Why alpha? The carbon atom adjacent to the functional group is known as what? Alpha, when the functional group is having carbon atom. So this is toluene is given and this is phenyl acetic acid. Now see the just see the reactant and products number of carbon atom. Here 6 plus 1, 7 carbon atom, and here how many carbon atoms are there? 6, 7, 8. So the carbon atom has increased by how many units? 1 unit. And whenever the carbon atom increases by 1 unit, there is one reaction, that is reaction of haloalkane with alcoholic KCN. There what happens? The product's carbon atom increases by 1 unit. So that is possible here. This when treated with chlorine in presence of sunlight, what do you get? CH2Cl. Now this has become a haloalkane. Now this you can treat it with KCN alcoholic. So here what will be the product? CH2Cn. And this on complete hydrolysis. In presence of acid, Cn will be converted to what? COOH. So is it clear? So for increasing the carbon atom by 1 unit, you can treat it with what? KCN. And that given compound has to be converted to what? Haloalkane. Now next is isobutyl bromide to tertiary butyl bromide conversion. Isobutyl bromide to tertiary butyl bromide. So let us make the structure. Isobutyl bromide. Next is tertiary butyl bromide. So this is tertiary. Now see here, in this question the number of carbon atom remains the same, here 4 and here also 4. But the condition is what you see here. Here the halogen atom is present in the first carbon atom and here it's present in which carbon atom? Second carbon atom. So the position of the halogen is changing, or when the position of the functional group changes, the given compound has to be converted to an alkene. And conversion to an alkene easy is haloalkenes can be converted to alkene. Same way alcohol also can be converted into alkene. So this when treated with ethanolic KOH, we'll get an alkene. See here. CH3, C, CH3, double bond, CH2, this is the alkene. Br will go from this alpha carbon atom and hydrogen will go from which carbon atom? Beta. Now see here, where is Br going? Br is going to the carbon with less number of hydrogen atoms. So its addition is taking place according to which rule? Markovnikov's rule. So you will treat it with HBr, you will get CH3, CH3Br. Now the reverse is also possible. That is tertiary butyl bromide can be converted to isobutyl bromide. Again here what are you going to do? Position is changing, so you will treat it with ethanolic KOH. Shall get CH3, CH3, double bond CH2. And then you will do what? Here Br is going to which carbon atom? Carbon with more number of hydrogen atom. So it will do which reaction? Anti-Marconic of HBr peroxide. So you're getting it? So this is how you have to do conversions. So to do the conversions, you have to be thorough with the reactions. So just practice all the questions in your textbook.